All right. So now go to a more general discussion. It's okay up to here. This is for this example. Now we can want to do something more general. And in this case, if you consider the whole domain, whole x from minus infinity to infinity, just the whole domain, and then subject to the boundary condition that psi is 0 at infinity, then you can forget about Laplace equation, the solution, because if there's 0 at infinity, then the psi must be 0 for Laplace, the solution of Laplace equation. So everything decayed away, decayed to 0, right? And now you can write down the more general solution. So let's consider 1D problem as your textbook did. So 1D problem psi, you have a psi xt, right? And but then subject to the initial condition psi xt, like a given function like psi 0. Right. We can now we want to solve for that. Okay, and subject to the boundary condition is psi x is infinity comes to 0. Okay, so that it should be enough to specify the problem. Okay, now what to do, or what method do you think we can do? It's not a trick question. It's just remind you what we did last week. What did we do? What method did we do last week in wave equation? Right, the last step. Right, we said that because we changed the order of the discussion, we have a powerful tool to solve this kind of problem. Yeah. Laplace is not we can probably use Laplace, but in this case I will use Fourier series, but Fourier series only in x, because that case we get back to just first order ODE in time, which is the solution will be quite trivial, right? So let's just use Laplace. I mean, Fourier transform. So phi xt becomes in 1D is square root of 2 pi, and phi 2 a b e to the I x, right? So then you can write down the equation for psi 2, which is now it's partial psi 2, because you know how to transform a second derivative, right? We put our minus k squared minus a squared k squared psi 2, right? Now the solution is straightforward, right? Right. So you remember? So what's the solution? Straightforward, right? Not harmonic, because this is first order. This is first order.
Yeah, pi equal to pi 0 exponential of minus.
Yeah, right. So minus whatever the coefficient, a squared, k squared. Everything decay away in time, right? So that would do it. And now you can put it back to here. Decide x equals 0. That is a function of k, because this is partial derivative. That is a function of k. E to the I kx minus a squared k squared dk. Right, that should be the solution. I mean, your textbook didn't use that, and I think it has the form of 9,102, which is exactly this form. Actually, if you look at that, because your textbook uses string choice using omega instead of k, usually we use K for spatial Fourier transform, right? But the textbook use omega, but the other formula is the same. And then he used cosine omega x and sine omega x, but we're using k, e to the I kx. Instead of omega, I use k. And then instead of cosine and sine, I use exponential function. Other than that, it's exactly the same as 9.102. Okay, and all right. Then, obviously, you need to figure out what this is. Because that's not complete yet. You need to use the initial condition. So set t equals 0, so psi 0x, which is the initial one, should be 2 pi, and psi 0 k u to the I kx, okay, which is exactly just the Fourier transform. I mean, the Fourier transform psi 02 is just the Fourier transform of psi 0x. And then you can solve for phi 0 k by the transform formula, right? We did that many times. What's this way, the psi 0x? Easy to do. Just need to change the sign. Right. So you do that and put it to here, then you get the solution. Okay.